All right, this is exciting. So thanks for joining, everybody. This is officially Ultralytics' first live session. This is the first in a monthly series that we're going to do. We are finding the best and most interesting companies out there, users and use cases with YOLOv5 and AI in general to highlight and to talk about. And today we've got Victor Snok here, or Sonk here from ClearML. Sorry for butchering your last name there. So Victor is a evangelist at ClearML. He helps integrate ClearML code and helps the community build amazing tools with it. So the general topic today is experiment tracking. Let's see. So experiment tracking in AI is important. I guess we'll start from the beginning. So I'm Glenn, by the way. I'm Glenn Jocker. I'm the founder here at Ultralytics, but I'm best known as the YOLOv5 guy. I got into AI about 3-4 years ago. I worked on YOLOv3 for a bit, kind of bringing myself up to speed with AI tools on that. And then when I tried to take it a step further, I ended up creating YOLOv5, which was open source like a little over 2 years ago. And it's gotten really popular. It's one of the most popular object detection architectures out there. But when I first started, I did everything manually. And when I was trying to improve models, I would run an experiment and I would kind of like jot down the notes on a piece of paper and then run another experiment, write down some more notes. And I'd realize that this was getting like a little bit untenable. So I was having difficulty keeping track of my experiments and figuring out kind of like what led to where, papers were getting lost and so on. And so I moved to a spreadsheet. I was in Google Sheets. It was really nice. But even there, eventually it was really hard and I was looking for something more automated. And in the last few years, like a crop of companies have come up to provide really cool integrated tools that automate experiment tracking. And now we've got some of these integrated right into YOLOv5. So if you train a YOLOv5 model and you have ClearML installed, then this will be automatically logged over to ClearML and you can go to your dashboard, see your results and compare it against previous results. So it's tremendously useful. And it's something I kind of wish I would have had like when I got started a few years ago.
Yeah, there's quite a lot of people that that might need it. Actually, even today, like when we go around and like talk to people or we stand on like ECCV or ECVPR, like the big computer vision fairs, even there you hear like continuously people saying like, yeah, Excel sheets is basically the name of the game. I've never quite heard someone saying that they like note it down on a piece of paper and like that's their experiment tracking. So you were very early. But Excel is definitely a big one there. And actually one that stuck with me, which is really cool, is like a dude that went as far as to basically like take all of their hyperparameters, put them in Excel, everything's fine. But then he wrote like a whole scripting pipeline behind that he could just like copy paste a new line and it would spin up automatically like a new version of his experiment and like override all the parameters based on what he put in Excel. And they would like pipe back to Excel. So like he built an admittedly very impressive, like fully functional experiment tracker like right into Excel. So yeah, there's definitely a need for it. You see that people want to use it, but there are tools that over time have been developed for this kind of thing. So it does make sense to use those instead.
Yeah, definitely. So I myself, I came over from the particle physics world and over there, we also ran experiments and reproducibility was also a factor. But I think it depends on the field of particle physics. Like in our field, we did have reproducibility problems, but it was for different reasons. So we would gather statistics on particles and we had low statistics. We can only gather like very few particles. And so different research groups would sometimes come out with different results, different error bars. And so in a lot of scientific disciplines, if you can't reproduce your results, then they don't really mean too much. And especially if other teams can't reproduce your results, then you might lose credibility as a researcher. So in ML, we also have this issue for slightly different reasons. So in machine learning, as I soon found out, a lot of operations are non-deterministic. So, all right, so in the field of statistics, we've got 3 different types of numbers. We've got deterministic numbers. So if you say roll the dice, you'll get the same exact number. And then we've got random numbers, which means that if you roll the dice, you'll get a completely different number. And then we've got something called stochastic, which means that you roll the dice and it's partly random, but partly deterministic. It's a little bit of a mix. And what I see with these machine learning trainings, for the most part, is that we get a stochastic result. So you'll have initial conditions with weights and biases, and then you train, and your training may diverge. And this is not uncommon in different architectures. Like, for example, PyTorch, in the early days when I started using it, it was completely normal to start with the same weights, the same biases, train the same model on the same computer, and end up with a different result. And now you might ask, right, like what's the magnitude of the difference? Because that's pretty important too. You know, if it's just very, very small, maybe it doesn't matter. But since we're trying to improve very small, then it does matter. Because, for example, if you, let's say, tweak the model, if you tweak the architecture, let's say you introduce like a new module, and then you retrain, and you get a result that's like 1% different. You can't tell if that 1% is statistically significant. You can't tell if it's due to random differences or if it's due to the change that you actually put in there. And so that does create a problem. And so even if the differences are slight, the improvements that you're seeking are also slight. And that creates a bit of a problem. And so there's different ways to mitigate that. And I think more recently, PyTorch has come out with some updates that improve deterministic operations. And they're available for most modules, but not all modules. But still, it's definitely a hot topic in the field, and it's something I didn't really like anticipate coming in. So.
Yeah, and it's also like but from the experiment tracking or like the QML part, like viewpoint, there's like more reasons that reproducibility are an issue. Like, so you have the non-deterministic stuff that you were just talking about, and that is definitely an issue. It's also something that, like you mentioned, the PyTorches of this world have to fix in like their own libraries, because it goes all the way down to the hardware, I suppose. Like I imagine, like, I remember like I run some experiments on CPU and GPU, and like GPU was always different, like just slightly, but then CPU was fine. So it's like stuff like
it's kind
that
of frustrating.
makes, yeah, it's super frustrating. Like it makes no sense if you're just like a data scientist and you just want to run this stuff. We're used to computers being like completely deterministic, right?
Yeah. It seems like they should be. I've looked into this a lot. Like I think it's sort of like a fundamental limitation with parallel processing, because I think it depends on like the amount of optimization that you're trying to seek, and if you're really seeking like the very last bit of optimization, then I think you have to be like willing to make some sacrifices on the reproducibility front. So it seems to be sort of like a bit of a trade-off. But you're right, it's really kind of like built into CUDA and built into like the NVIDIA hardware that we're using. And so in some senses, there's like not much you can do about it. But this is why it's like doubly important to be able to, I think, just have like a single spot where you can look at your results, but also share your results. And so when we talk about reproducibility, like what we typically talk about is maybe yourself trying to reproduce the same result, but more often like someone else.
Yeah.
Exactly. So in academia and here in ML, we'll publish a paper. So I have published papers before. YOLOv5 doesn't have a paper yet. A lot of people ask me. Why not,
actually?
It's this is like the reason is because we have finite resources and we have to dedicate them all to R&D and to moving forward, and to kind of like explain what we've done takes time. But the second reason is also that YOLOv5 isn't set in stone. And so we don't really have a great opportunity to kind of like stop, take a look back and say, okay, like now we have some free time. Now this is YOLOv5, it's not going to change. Let's invest the effort in explaining it. Because the reality is every few months, so every few months we have like new architecture changes that are inspired by new R&D, new publications that we see. And so if we did publish a paper, we'd also have to keep releasing new updates to the paper, just like we keep releasing new updates to YOLOv5. And unfortunately, like we've got a really small team. So Ultralytics itself, it's less than 10 people. We're mostly in Europe, but you know, we're not like a really big funded group. Like we don't have like a big VC back or anything like that. So like we're really kind of like punching above our weight here and doing a lot of stuff with a few resources. And so that's basically the reason we don't have a paper. I'd love to create one, and I have written them in the past. I've got a lot of physics publications.
I can imagine.
And I think one AI one. I just haven't had time to really write the paper that I want to write. So.
Yeah, okay, that makes
But
sense. And like when you're talking about these papers and like other people reproducing your results, I think apart from that non-deterministic stuff, I think there's like one more thing, and that's just keeping track of
yeah,
everything. Like just simple the same package
yeah,
version
yeah,
on like the same environment or like the
yeah,
same
yeah,
system packages, like
exactly.
stuff like
Yeah,
that
yeah.
is much easier or like easier to track because it's not hardware level, but it
Mhm.
still is a significant like when is the last time you went to GitHub and like went to one of the like purely academical repositories and the requirements.txt like install from the first time? Like almost
Yeah,
never.
everything works the first time. Yeah, yeah. This
And
has been
so
my dream in ML is to kind of do what Steve Jobs said and have it just work. Of course, that
yeah.
like we're not there yet. I don't think we're
Oh
close,
no.
but like that's been the direction I've been trying to go. But you're right. Like it's a big problem. Environments. So I came from MATLAB actually, and
Oh.
MATLAB is like a nice walled garden and things work there, but it's not if you want the latest research, like you're never gonna find it there. And so I migrated away. And I'm
Mhm.
like really glad I did. But now in the Python world, of course, it's more like the Wild West. Like it's up to you to set up your environment, find your packages, make sure they're playing well together, make sure you're like on the right commit if you're downloading or you're cloning a Git repository. It's really there's a lot of things that can go wrong. And this is a big place that experiment trackers can come in. And so it's not just about seeing the final result, but it's about going back to the beginning and
Yep.
seeing what people did to create that final result. And so
Yeah,
that's the big
exactly.
thing about experiment trackers. You get both of that.
Yeah, and there's also a relatively low incentive for people to actually keep track of that because you can actually do it. Like you can keep your requirements.file up to date. You can keep a Docker file with everything inside just right next to your code. It's just people don't tend to do that. So like one of the things that ClearML tries to do as much as possible is like
Mm-hmm.
like to automatically track as much as possible, right? I remember like
Mm-hmm.
a comment on Reddit that said like we moved away from ML flow, for example, because you have to remember to manually add your git tag or like your git commit hash as a
Oh, okay.
parameter like in the
Yeah.
experiment tracker. Like you don't want to necessarily do that. I don't know if they still do it, by the way, but like that was something. And you want to try and capture of that kind of stuff as much as possible. So for example, when you go into the ClearML experiment manager, you run it with YOLOv5, for example, you'll see all of the
Mm-hmm.
packages that were actually installed in your environment and not necessarily your requirements file. But the same thing with like a
Oh,
Docker
okay. Yeah.
file, same thing with like a Docker
Okay.
file that you want to add or
Mm-hmm.
uncommitted changes. Like there's no real
Mm-hmm.
reason sometimes to actually commit like the smallest change in hyperparameter because
Okay.
unlike like previous like normal software engineers, they always have this commit trigger, I call it. It's basically you start working on something and then at some point you think, okay, like it
You
works, I have
decide
to
it's
test
yeah.
it, but I decide like this is the bulk of the stuff done. I add a commit,
Yeah.
this is my commit trigger.
Yeah.
But there's no real thing like that in data science where you can say like this metric is like high enough
Oh,
now,
yeah, yeah.
right? It's
Yeah,
like
yeah.
I'm always searching for like the next
Huh.
gain in performance or like the next step. So
Yeah,
it's
yeah.
much harder to keep track of that in Git, which is why an experiment manager tries to do that. And we like automatically capture your
Mm-hmm.
Git hash, automatically capture any uncommitted changes as well, and then like all
Mm-hmm.
of the outputs, of course, like plots and debug samples or model files, stuff like
Mm.
that.
Yeah, yeah,
So
yeah.
yeah, and like we try to hook in to as many of these libraries as possible. So for example, if you use PyTorch, like YOLOv5 uses PyTorch,
Yep, yep,
um,
yeah.
then we'll automatically detect like, okay, you're using PyTorch. So whenever you're running torch.save, we'll basically hook into that and also send it to ClearML, right? You can
Mm.
of course
Oh,
disable
okay.
this, but
Yeah.
that kind of allows you to just jump in, forget about all the rest, and then just
Mm-hmm.
start working with just 2 lines at the beginning, and then just not bother
Oh,
with
wow.
anything else. Yeah, that's kind of the goal. I mean, it's not perfect. Nothing is
Yeah.
perfect, but that's kind of the idea.
That's really cool. So you can actually is that called monkey patching where you kind of
Yeah,
like go into
yeah,
the package? Yeah, okay,
exactly.
that's
Like
sort
you
of like
basically
the yeah,
overload the functions. It's actually a really cool code as well to dive into.
that is really cool. Yeah, yeah, okay. So that allows you to add all this capability without the user having to like add additional lines of code into their
Yeah,
project. Okay.
basically. I mean, it's not perfect. Like one example is matplotlib. Matplotlib is the same thing. So we
Mm-hmm.
kind of overload the plot.show
Mm-hmm.
method, where you basically say like instead of just showing it, like also capture the actual plot and like add it to ClearML. But then you have to kind
Mm-hmm.
of we use Plotly, which is like interactive. So you want to
Yeah,
make it
yeah.
as interactive as possible. but then you have to convert between like matplotlib and plotly, and that can
You try and
sometimes
do
get
it.
hairy. Yeah. So either you get like an
Okay.
inconsistent plotly graph. I mean, most of the time you'll get a perfectly fine one, but like there's edge cases obviously, and then sometimes you get like an imperfect interactive one, or you get it as an image, and then you can just
Oh, this is
like
cool.
zoom in on it, but it's
Yeah.
not interactive anymore.
Oh, so I didn't realize that's okay. So ClearML is using Plotly like inside. So like when you upload like a matplotlib, or when you just plot with matplotlib, if you have ClearML installed, then you'll see that as an interactive version in your ClearML dashboard.
Depending on which plot you do, yeah. But you also have like the manual plotting functionality, and it's basically like a wrapper for Plotly. So you can always add stuff yourself. But then things like scalars are different. So this is like, for example, for like a confusion matrix, right?
Yeah, exactly.
But then
Exactly. Yeah.
but then you have like
like
scalars as well.
like a class histogram or something like that.
Exactly, right. But then you have like scalars as well, and these are basically just the one number you log every iteration, and that just get automatically built into a graph, which is Plotly based. Yeah.
Okay. Yeah, that's really cool. Yeah, I keep thinking back to physics here. So in physics, we have the same theory essentially. So if a system has initial conditions, and if they're known, then you can reproduce the system given the same initial conditions, like in theory. And I say in theory because
quantum mechanics might disagree.
Well, exactly. Yeah. That's what I was going to say. Yeah. So we don't really know, and this is actually like applicable in everyday life, because we don't know if we really have like free choice, like if there's randomness in the universe, or if everything that we're doing right now, like this conversation, for example, could be reproduced just given the initial conditions of the universe. Like if we start the universe all over again, will the same exact thing happen? So reproducibility even is at like the core of everyday life, and like we don't really know like if what we're doing is reproducible, or if we go back in time, we'd have a different conversation. So it's really, really interesting stuff. So ML has parallels, with real life and with particle physics and with a lot of other things, I think.
Yeah, it's this kind of weird dichotomy, because I always think like when people say, yeah, an AI is like built as a brain, like, no, it's not. But when you look like reinforcement learning, there's like several things that actually do make sense if you look at a human, and it's like relatively similar. So yeah, sometimes it's like very close to reality, and then sometimes it's like, no, it's just
sometimes.
It's just,
yeah. Like it's like when you look at a model, it's like clearly not structured like a human brain. But maybe if you take a step, like if you abstract away the architecture and you sort of look at like the results, then there's some behaviors that are strangely similar. Like for example, when I first got into AI, I had a model and I had it doing like one task, and it was performing well. And then I added a second task to the model, and it performed slightly worse at the first task, even though it did both tasks. And I thought, so I kept trying to work at it, trying to bring the performance of the first task back. And I started asking people, and someone said, no, that makes a lot of sense. If you have like a finite set of resources like the brain, and it has to do more and more things, it's not going to do as well in each one, right? That's just called multitasking. And people always argue about that. They're like, oh no, I can do all this at the same time. But then I think in reality, like you can't. Like the brain has attention, and the more things you try, like if I try and like code with two hands at the same time, it's not going to work very well. And the models perform the same way. As you add more classes or more tasks, given the same like size model, it's going to perform slightly worse at each task. And so in this sense, like there's definitely parallels between biology, anatomy, and machine learning, even if just kind of like at a high level.
And so when you were working on the particle physics stuff, like did you have access to HPCs, like large compute clusters that you could play with, or was it not that kind of research?
We did, but so this is at the University of Hawaii with the particle physics group there. They're best known for the satellites over like Mauna Kea and Mauna Loa, but we were doing anti-neutrino physics, and the group wasn't really ML focused, and so we did have computer clusters, but they're all CPU clusters. So so they weren't like particularly useful for ML applications. And also even aside from that, most of the ML I did there was sort of like my own hobby, because when I talked to the professors, there's a bit of a culture issue in that I'd show them like the latest research, I'd try and get them excited, but they just weren't, these were like old professors, like 65 years old. They've been in physics for a while. They had certain techniques that worked well, just kind of like the classical statistics, like fitting, like Newton's method, and they said this has been working for like 50 years. There's no reason to change it. And so I couldn't kind of like get around that culture. So
yeah, okay, that actually makes sense.
but the other big reason was that we just didn't have any real world training data. So to train ML models for these particle physics experiments, like to detect particles, figure out where they're coming from, you need a lot of real world examples. And I use simulated data. It did not work very well. It worked well in the simulation, and then I turned around, applied to the real world data, and then it was a big disaster. And this is like another interesting thing you still see like in the news. Like there's companies in the AI space like Waymo that are like heavily reliant on simulated data, and then there's other companies that kind of prefer maybe a mixture or more heavily weighted towards real world data like Tesla. And so this is another debate that's kind of like open-ended and never really seems to have an answer. So
yeah, no, that's like the domain transferability, right? The domain adaptability. It's like, will it work somewhere else? But it is like it's a complete research topic on its own. So I kind of get why you couldn't really get it to work on your.
There's so many fascinating topics around here. But yeah, you're right. There's like slight differences between simulation and reality that may not be apparent to us, but that the model picks up. It sees like some slight variations, some differences, and those kind of add up to
or
produce
an
a different
FPS counter.
Yep. But like so I've been pretty lucky, at least like in the vision space, like we don't have that problem. We have a lot of real world data. So now I don't have to think about it too much. But
true.
But I guess even in the vision space,
I think even in the vision space, like there were edge cases, and so you had these people. I remember they used like GTA 5, right? They had like a whole data set in GTA 5, just hooked into the shaders on the GPU and just like used that data because it's already semantic segmented, right? So you know the classes of everything, so you can just extract it. Yeah,
and the game engines are getting pretty realistic too. So.
Exactly. Imagine being a PhD student and being allowed to just drive around in GTA 5 getting some data. That'd be pretty cool.
Yeah. Just playing video games. Professor's like, what are you doing? You're like, can't you see I'm working here?
Yeah, exactly. And so, but like when you're now currently working on YOLOv5 and like you're constantly experimenting, like are there like large GPU machines that you're using, or like how do you do that orchestration stuff?
Yes. So we burn through a lot of cloud credits. So Ultralytics, we applied to Google and the big cloud providers like Amazon and Microsoft, and we used all the cloud credits that they had to offer, except for Microsoft. We were like really confused by Azure Cloud, and I still can't get it to work. But after that was done, our R&D kind of ground to a halt, and we needed to run more experiments. And so we ended up investing in a server, and we got this from Lambda Labs, and it's called Colo. So we didn't actually take delivery, but they put it in a server center somewhere. And so now we have this instance with 8 GPUs, and we run experiments on it. I SSH into it. And this is still a bit of a manual process for me. I'm kind of embarrassed to say. So,
no.
And I still use pieces of paper. So I use experiment trackers to keep track of the experiments. But when I come up with experiments, I usually just kind of like jot ideas down on a piece of paper, and I'll just put a number like 0 through 7 on the experiment. And then when the resources free up, I'll just SSH in. I'll construct some commands manually, like Python train.py, this and that. And then I'll just sequentially kind of like run these. And so the tracking part of my workflow is pretty automated. I think it's pretty optimized. The sharing part, the reproducing part, but the setting up of the experiments, and I think utilizing resources well is something that I'm not doing as well as I could. And utilizing resources is pretty important. So for example, if I go to sleep, I wake up, I can see that there's some free GPUs that have just been sitting there idle, like while I've been sleeping, which is not ideal. So if I was, I think a better data scientist, I'd figure out a better way to do this. And I know ClearML does have like tools for that. You guys call it orchestration. Could you talk about that a little bit?
Yeah, so it's basically indeed the orchestration component. Like there's several ways to go about this, right? So when I ask this on things like CVPR, we always indeed get like SSH, but at least now you are like the only one running on these 8 GPUs, or like at least one of the only ones. But then there's like PhD students that have to share it with like 10 others. And on the same machine, if like another person SSHs in, like they kick themselves out, or like they go out of memory or whatever, and they shut themselves off, or like they shut down like other processes that are continuously training because like they use too much VRAM or anything. So that's kind of, there's like multiple ways to do that. But if you have a machine on site, I think ClearML has like a nice approach to that, which is basically queues and workers. It's like the very well-known paradigm where you have like a bunch of queues that you can define yourself, basically. And then you have a number of workers, which are just processes that can connect or like listen to these queues. And the cool thing I like to talk about is basically when you're using ClareML as an experiment manager anyway, like I talked about before, we already have all the install packages. We have the git commit hash. We have the uncommitted changes. Like we have the Docker container. So if you have all of this information, what you can then just do is say, okay, like I have any of my already tracked experiments, and I can just clone one of those. I can change the hyperparameters just from the UI, and then enqueue that or like put that into one of the queues. And then in this way, you can like easily clone 7 new experiments, change all of the parameters, throw them into a queue, and they'll just wait there until there's room on the GPUs to be executed.
Yeah.
So like
This is
while
really
you're
cool.
sleeping, it's just like neatly like taking down the stack.
What
then,
if one of the experiments is like a multi-GPU run? Then what if like only one GPU frees up? Like, does it wait until there's the right amount of GPUs freed up to? Like, do the other ones bump up in the queue if there's single GPU runs?
It's a kind of thing you can actually select yourself. So like, for example, changing priority is relatively easy. Like you can just like drag and drop the task in a different spot in the queue. But what we see like people use is every queue can be attached to basically, like you can basically define it yourself how you want to do it. Like it's kind of a neat thing. So for example, what we see people do is they have like a single GPU queue and a multi-GPU queue. And then the multi-GPU queue is listened to by agents or like workers that have access to multiple GPUs at the same time. And then you have a single GPU queue that is accessed or like that is monitored by workers that only can access one GPU at the same time. So you could have on a single machine, you could have like 8 single GPU workers running, listening to the single GPU queue, and then you could have like 2 4 GPU workers running on the same machine. And then you still have to share the GPU memory. So that is still like a limitation. You will have to figure out for yourself like where to put the limit. But in that case, you know, like as a data scientist, you know, if I'm putting it in the single GPU queue, it will be executed on a single GPU. Otherwise, I can add it into the multi-GPU queue, and a worker with multiple GPUs will take care of it.
Okay, that's really cool. Okay. By the way, I forgot to mention here for the audience, we have a Q&A session. So if anybody has any questions, feel free to let us know. I guess like we're open to anything at all here. So like one more question, Victor, about this orchestration. Let me see here. So is there a way, so a lot of my experiments, sometimes I tweak hyperparameters, but sometimes I also need to customize more. And when I do that, I'll usually change the code and save a new commit in an experiment branch. Is there a way to like set I guess like a Git repo, maybe branch and commit in that orchestration queue?
Yeah, for sure. Actually, it's good that you mentioned this because I was literally last week, I was working on like 3 example GitHub CI/CD actions. Small plug, you can actually find them in the marketplace now. So that's kind of neat.
Cool.
But yeah, the cool thing is like everything that I just mentioned, like the orchestration and adding them to the queue and everything, the whole control plane of that, or like the API to that, is all in the pip package. So it's actually relatively easy to like add a small Python script as a GitHub action that basically triggers on whenever you do a commit or like whenever you do a merge of a specific branch, to then have the GitHub Actions worker actually spin up new experiments based on the code on these agents. And actually, there's actually even more things you can do with that, because these agents, like these workers that are listening to those queues, they actually have GPUs available as well. So we see that people are, we see that people are actually using, this connection or like these workers as basically test beds, because sometimes, especially in like machine learning, you want to run PyTests or like tests on GPUs as well, and then you can actually
This is a big problem that we have actually. We've got a lot of CI in YOLOv5. It's really helped some things out, but
it's actually really nice as well.
Yeah, but we need that also on GPU, and I haven't found the best way to do that yet.
So
I've
one
seen
way
that there's
to
like
do
custom runners and things like that.
Yeah, so one way to do it would be like basically using the GitHub Actions worker as like a controller or like a control plane, and then they would basically spin up a new machine or like add the tests in the queue, which could be like a tests queue, which gets only like limited open availability GPUs or whatever. You could add it to the test queue. They would just be run down, and like the machine would continuously be running tests basically. And then the GitHub Actions worker would basically just pull the change in status of the task. So for example, one thing that we do is, or like that is—
Victor, let me interrupt you here real quick. I just looked at the clock here. It looks like we've used up our 30 minutes. And
sure,
I haven't
no
looked at
worries.
the question list. Yes, let's see. I see one from Talia that I'll answer real quick, and I guess we'll wrap this up since this is technically a 30-minute session. So Talia's asking kind of like what the future things we might see in the partnership are. And one thing I forgot to mention here too is that I recently worked with Moses at ClearML to integrate like a much better way to run our Colab notebooks. And so now ClearML has like a much more integrated system. And so if you're logged into ClearML anywhere, like in the browser, then your Colab notebook will just automatically detect that. And if the pip package is installed, it'll automatically log to your account. You don't even need to log in on the Colab notebook. And this is a super cool step. This really, really helps out workflows, I think. It means that if I wake up tomorrow, pull up the same Colab notebook, run the same code, I won't need to log in. So this really automates my workflows. But in terms of next steps, I'm not sure. I think like we're going to keep things coming, and I think probably like do some more of these webinars. But I think also like the important thing is like we'd like to hear from the users what you guys would like to see, what the pain points are, so that we can work on those and address that, because I think that's really important. I've got my own kind of like ideas, but I think the community is really important. And I think hearing from everybody else what they're doing is tremendously useful. And it's really helped kind of get us where we are today. So feedback is super important. So if you have any, feel free to leave it on the YOLOv5 repo or the ClearML repo, or just like contact us any other way on social media. So
yeah, even as an angry issue, we always look at them.
Actually, yeah. Like the bug reports are the most useful, actually. So
yeah, they are.
So positive,
they're
positive feedback isn't actually that good. Like I can't really do too much for that, but like negative feedback is actually really informative. So that's my favorite kind. Okay, all right, guys. I guess we'll wrap this up. So Victor, thanks a lot for your time, and everybody else out there, thanks a lot. Yeah, and have a great week. Okay, bye.
Bye-bye.